Hello, AP. Today's lesson is covering sections 8.9 to 8.12, okay? And the topics are drawing Lewis structures, tying in resonance and formal charge to the Lewis structures. So again, we're dealing with models, okay? And so when we are talking about our Lewis structure model, okay, we're going to look at what are called lone pairs and bonding pairs of electrons. These are all the valence electrons, and they're the electrons that are found in the s and the p orbitals. Okay, so that's what this is referencing here, the s and the p orbitals. Okay, so let's keep going. All right, so a lone pair now is a pair of electrons that are not being shared, and we're going to symbolize the lone pair by using dots. Okay, so let's see if I can get my pen. Okay, there we go. Okay, so lone pairs, dots. Okay, bonding pairs, those are the electrons that are shared between the atoms. We're going to use dashes to represent that. Okay, so now what the Lewis structure is, it's showing the arrangement of the valence electrons around each of the atoms involved in the molecule. The reason we draw these Lewis structures is so that we can predict the geometry, which is the shape of the molecule. And the reason we want to know about the shape is because that determines how the molecule will behave chemically. Okay, so in the next lesson, we'll look at what's called the Vesper model. Okay, and again, dealing with shared pairs and lone pairs, so dashes and dots. All right, so the Lewis structure now will have a central atom and then outer atoms bonded to that central atom. And the goal is to fulfill the octet rule, which means we want to be like the noble gases. Oops. Oh, yeah, that was right. We want to be like the noble gases, okay, with that S2 P6 configuration, 8 valence electrons, okay? And so we have to look at hydrogen as an exception because hydrogen only has an s orbital, so it can only share 2 electrons, and it doesn't have a p orbital, okay? And so we'll show that by the dots between the atom, but we would also prefer to use a dash instead of a pair of dots, but you can tend to see a pair of dots as well. Okay, and then we have a diatomic molecule like fluorine, which will fulfill the octet because it has an s and a p orbital. Okay, so there's our hydrogen molecule, and see there's our shared pair drawn with a dash instead of the dots. We like to save the dots for the lone pairs. Okay, now sometimes we may have to use a double bond because we don't have enough electrons left to fulfill the octet. And that idea is coming up in the slides down the way, okay, as well as the triple bond here. Okay, so when you don't have enough electrons, then you have to share. And so when we draw these structures, I'll explain how that double bond and how that triple bond come into play. Okay, now this is not the slide I had, but these are the steps for writing the Lewis structures. Okay, so you first add up all the valence electrons from all the atoms, okay, so that you know how many electrons you're working with when you go to draw the structure. Okay, then you're going to put a bond between each of the atoms that are bound together, and you'll draw a dash to show that, and then you'll complete the octets by drawing dots. Okay, so I'll kind of explain that along the way. Okay, so here's water. We're using water. Now this isn't necessarily the best one to start with, but it works. Okay, so we've got hydrogen. Okay, and hydrogen has 1 valence electron, but there's 2 atoms of hydrogen, so we're dealing with 2 valence electrons there, and then oxygen has 6 valence electrons. And remember, the shortcut to getting the valence electrons is look at what family it's in and use the A values, okay? Because the A values are the valence electrons. So oxygen is in group 6A, so it has 6 valence electrons. Okay, now we're going to bond them with dashes. Okay, I'm going to draw it over here. And I'm drawing it bent because I know it's bent. Now you maybe don't know it's bent yet, but when we get into valence shell electron pair repulsion model, that's where you'll learn about these different structure shapes. Okay, so there's our shared pairs. So we've used 2 electrons in each of these sharing situations. So a dash represents 2 electrons. Okay, and then in the third step, you show the dots by fulfilling the octets on the outer atoms. Now hydrogen's octet is already fulfilled. See, it's got 2 here and it can't hold anymore, so we're not putting any dots around that atom. Okay, so what we would have to do is then, since hydrogen doesn't have any dots, we would have to place the dots on the central atom, and there's 4 left. Okay, so these are lone pairs and these are shared pairs. Okay, so there's our 2, 4, 6, 8 electrons completing the octet rule. Okay, so you can try that with each of these. Okay, so we did water. We could do the same thing with phosphorus tribromide and hydrogen cyanide. But you try it, and then I'll insert a clip explaining why the model is the way it is, because the slide will bring up the answer. So there's water, there's phosphorus tribromide, and there's hydrogen cyanide. Okay, and so I'll insert a clip after this and explain how those were drawn. Okay, now here's another concept check. There was our hydrogen and our fluorine from our beginning slides. Okay, so you could try and draw them, and you could try and draw hydrogen fluoride. And again, I'll insert a clip so that you can see how those are drawn. Or actually, I could probably draw these right now. Hydrogen has 1 valence electron. Okay, and fluorine has 7, so that's a total of 8. Okay, so we've got our total valence electrons. Now we attach them with a dash. Okay, I've used 2 electrons so far. I've got 6 more left. The next step says fulfill the octets on the outer atoms. So I'm doing that. 2, 4, 6, 8. There's all our valence electrons, and here's our drawn hydrogen fluoride molecule. Okay. Right, here's a chance for you to try 3 more. Okay, and then we should even maybe try an ion, like let's see, the carbonate ion. We could try that one. Okay, so you try them, see what you come up with, and then I'll insert a clip showing how to draw each of these.
Okay, now the trick to drawing Lewis structures is to just get used to that set of rules and follow them every time, and then you'll always draw the structure correctly. Okay, so here's kind of an additional set of rules for you to put into your notes. Okay, so when you want to draw the Lewis structure, you want to add up all the valence electrons for the elements involved in your molecule, and then put the least electronegative element in the center, and that's usually the first element in the molecular formula anyway. And then you want to attach all the other elements to that center element with a dash. The dash represents 2 electrons. Then place dots on the outer atoms to complete the octet. The leftover electrons, if there are any, then get placed on the central atom. And if there's not enough electrons to complete your octet, then you use multiple bonds. Okay, so here's how ammonia was to be drawn. Okay, so I'm counting all my valence electrons. So nitrogen is in group 5A, so we've got 5 valence electrons for nitrogen, and hydrogen is in group 1A, so plus 1, plus 1, plus 1. So we're dealing with 8 electrons. Okay, so you want to keep track of the electrons by counting up as you're adding dashes and dots. Okay, so first we put our N in the center because it's the least electronegative, and then we put, actually, hydrogen might be more of a not so electronegative element, but hydrogen can't have more than one bond, so it couldn't be a central atom. Okay, so we've got nitrogen in the center, and then we're attaching the other elements with a dash. So far I've used 2, 4, 6 electrons. So I've got 2 electrons left to place. Now the next rule says place the extra electrons on the outer elements to complete their octet. Well, hydrogen's octet is 2, so it's already complete. So then we move on to the next rule, which says any leftover electrons go on the central atom. There's 2 electrons left, okay? And we've now used up all our electrons. So the valence electrons have been placed, 2, 4, 6, 8. Octet has been completed, and so that's the Lewis structure for ammonia. Okay, here's CO2. Okay, so let's draw the Lewis structure for CO2. So first of all, valence electrons, 4 plus 6 plus 6 gives us 16 electrons to work with. Carbon in the center, oxygen attached outside. And again, it doesn't matter where you make the dash. You could have put it up this way if you want to. You'll get a better understanding for the shape when we get into the next chapter and we talk, or the next lesson when we talk about the Vesper model. All right, so we've used 2, 4 electrons so far. So we've got 12 electrons left. All right, next step says complete the octets on the outer atoms. So I'm completing the octet, 2, 4, 6, 8, 2, 4, 6, 8. So I've used 2, 4, 6, 8, 10, 12. I've used 12 electrons. I have no electrons left to work with. Carbon does not have a complete octet, so I have to now go to the last step that says use multiple bonds. So now I'm going to push these 2 electrons down here, okay? And so that now means that those 2 electrons are no longer belonging just to oxygen, but now they're shared between carbon and oxygen. So oxygen still has its octet, 2, 4, 6, 8, but now carbon is getting its octet, 2, 4, 6. We're going to push 2 more down here. Okay, and so now 2, 4, 6, 8, oxygen's still content, and now carbon is happy too. So this would be the Lewis structure for carbon dioxide. Okay, and then carbon tetrachloride. Let's see, 4 plus 7 plus 7 plus 7 plus 7. Okay, so 28 to 930 to 132 electrons. Yep. Okay, carbon in the center. Okay, attach the other atoms with a dash. 2, 4, 6, 8. Okay, we've used 8. That leaves us with 24. Okay, complete the octets on the outer atoms. Remember, the dashes or the dots are lone pairs, the dashes are shared pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's all 24 electrons placed on the outside. Carbon has its octet as well, so this is the completed Lewis structure for carbon tetrachloride. All right, now I think we should do an ion as well. Okay, so if you have an ion, you follow your same rules. Okay, you continue with these rules, but when you sum the valence electrons, you have to add electrons in if it's a negative ion, and you have to remove electrons if it's a positive ion. Okay, so we're going to try this ion. This is the chlorite ion. Okay, and so we've got 7 for the Cl, we've got 6 for the O, and there's 2 O's, and then we've got 1 extra electron because it's an ion. So it looks like we've got 12, 13, and 7. It looks like we're dealing with 20 electrons. Okay, so same steps. 2, 4. Okay, I've got 16 left. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we've got 4 electrons left. Octets are completed. Okay, leftover electrons go in the central atom. Okay, we've used up all of our electrons. All the 20 valence electrons have been placed, but this is an ion, so when you have an ion, you put a bracket around it, and then you put the charge outside of it. And so there's your chlorite ion.
All right, now we hit some exceptions to the rules. Sometimes we can get more than 8 electrons in our octet, and sometimes we have less. Boron tends to be one of those compounds which has fewer than 8 electrons around it, and so that makes it very reactive. So it breaks the rules. We can see that it only has 6 electrons instead of 8. Okay? Beryllium is another element that tends to do that. Okay? But all the other elements in that period, they fulfill the octet. Just beryllium and boron tend to break the rules. And we also have, as you can see, more than 8. We have 34 valence electrons, so if we count, we have 2, 4, 6, 8, and then we fulfill the octets, and we find we have 2 electrons left over, so we put those on the central atom. And so these exceed the octet, and the reason they can do that is because of that d orbital. All right, so here's some exceptions. So you can try and draw these structures and see how you do, and then I'll insert a clip and show you how they're drawn.
Okay, let's look at some Lewis structures that are exceptions to the rule, meaning they break the octet rule. So if you recall, beryllium and boron of group 2, the second period, they tend to have less than 8 in their octet rule. And that makes them very reactive. Okay, but the other elements, carbon, nitrogen, oxygen, and so on, they fulfill the octet rules. So how does this work? So we still follow the steps. So let's see, boron has 3 valence electrons. Fluorine has 7, and there's 3 of them. So there's 21, 22, 3, 24. All right, so we're dealing with 24 electrons. B would be your central atom, and then F would be attached with a dash, 2, 4, 6. So we've used 6. Okay, we've got 18 left to deal with. Complete the octets on the outer elements. 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used all 18 now, and boron octet is not complete. It only has 6, and that's what makes it very reactive. Now, yes, we could push 2 electrons down, but boron doesn't tend to do that. Okay, so this is one of the exceptions to the rule. Okay, here's another one. Okay, let's see what happens. So phosphorus is, let's see, 5, and chlorine is 7, and it's 5 times, so we've got 35. Looks like we have 40 electrons to deal with. 5 and 7 times 5. Okay, so phosphorus in the center, 1, 2, 3, 4, 5. Okay, 5 chlorines. Already you can see the octet has been broken, but we still follow the same steps, 2, 4, 6, 8, 10. So we've got 30 electrons yet to deal with. Complete the octets. Oh, I wonder if I use them out. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Sure enough, I did. So, octets are fulfilled on the chlorine, but phosphorus has more than 8. And that's because phosphorus has a d orbital. So it can actually do this. Okay, that was phosphorus pentachloride. All right, sulfur is another one that breaks the rule and will tend to have more than 8 valence electrons. Okay, so sulfur has 6, and then there's our fluorine, 7, and there's 6 of them. So we've got 42 and 6, 48 electrons this time. Okay, sulfur in the center, 1, 2, 3, 4, 5, 6. So 2, 4, 6, 8, 10, 12. We've used 12. We're left with 48, 38, 37, 36. Okay, octetting. I wonder if that's a word, octetting. Sounds like it. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. We've used them all, and so there is the Lewis structure for sulfur hexafluoride, and it's an exception to the octet rule.
All right, so quick review. So all the rest of the elements, carbon, nitrogen, oxygen, and fluorine, they'll obey the octet rule. Just boron and beryllium will not, okay? And then our second row, they never exceed the octet rule because they don't have a d orbital. And then our third row and up, they can break the octet rule and exceed it because of the d orbital. Okay, and so when you draw Lewis structures, try to fulfill the octet rule first. And then if you have leftover electrons, okay, they go on the central atom, and that's because they have d orbitals. Okay. Now, what happens if you have an option where more than one Lewis structure works? So if we were drawing this ion, has 24 valence electrons, we see that we would attach these with single dashes and then fulfill our octets, and then we see we've run out of electrons. So we have to take a pair off of one of the oxygens and share it. There's our multiple bond situation. But notice that we have 3 oxygens to choose from. So which one do you choose? Well, resonance means that it's possible that you would have a blend of all 3 of these. And so the actual structure is not this, not this, not this, but the blend of all 3. It's kind of like if you took blue paint and yellow paint and you mixed them together, you got green paint. And so the green paint has its own identity because it was a blend of the other 2 paints or molecules, if you will. Okay, so that's what resonance is it's showing all the possible options that can be drawn. And then you use this arrow in between them to show that it could be this, this, and this, and so it's really a blend of all 3. And then notice it's an ion, see the brackets. They enclose the molecule, and then you put the charge on the outside. So this is one of the examples of resonance, and there are other structures that can also be drawn like this. Okay, so the point to remember is it's a blend, and that's because the electrons are really delocalized. It means they don't belong to any one atom. They can be moved around the whole molecule. And so that's what the term delocalized means, where localized means it belongs to that one atom. Okay? So here are examples of some more molecules to try. We've got an ion in here. Okay, and I know we've got some double and triple bonds going on, so these are some more good practice molecules. And then I'll insert a clip to show you how to actually draw these.
All right, so let's do a little more Lewis structure review. So this is carbon monoxide. So I'm going to count the valence electrons. 4 for carbon, 6 for oxygen. So we're dealing with 10 electrons. Okay, so there's only 2 elements, so there's no central atom. All right, I've placed 2. So I have 8 left to deal with. I'm going to complete my octet. 2, 4, 6, 8. Okay, I've used them all. Now I see that while oxygen has a complete octet, carbon does not. So we've got to use some multiple bonds. So I'm going to push these 2 over here. So now they're being shared. Okay, oxygen still happy, content with its 8. Carbon not yet. So we got to push 2 more. Okay. And so that's going to give us a triple bond. So we're going to end up with carbon with a triple bond, and then a set of lone pairs on each element. So there's carbon monoxide. Okay, here's an alcohol. This is methanol or methyl alcohol. Okay, you probably can already see the structure for this one. And so what would be the central atom? Okay, well again, this would be the central atom. Okay, so you'd have carbon on the center. Okay, and we could count all the valence electrons first. So that'd be 4 plus 3 plus 6 plus 1. So it looks like we've got 14 electrons. Okay, so I've got my 3 H's on my carbon. And so this is an organic compound. That's the methyl group. And when we get into the organic chapter, you'll get used to drawing substituents in these carbon chains. You won't be counting valence electrons. Okay, so we've used 2, 4, 6. Okay. All right, so we've got 8 left. All right, and so 2, 4, 6, 8. Actually, we've used 8, so we've got 6 left. Okay, and so we're not going to put the hydrogen here, because then what do we do with this oxygen? Okay, so the oxygen is what must be bound next. Okay, and then that hydrogen is going to have to be bound to the oxygen. So it's kind of like it's laid out. And then, of course, octets have to be completed. So let's see how many electrons we've used. We need to have used 14. 2, 4, 6, 8, 10, 12, 14. We've used all 14 in our Lewis structure. Okay, and this is an organic compound. All right, here's carbon dioxide again. So this one's here to review the formal charge concept, because really carbon dioxide can be drawn 2 completely different ways. Okay, so let's get our total electrons. So it looks like we're dealing with 16 electrons, 4 and 6 and 6. Okay, and so carbon is our central atom. Okay, and we've used 2, 4. So that leaves us with 12. So we're going to complete our octet. Okay, and that uses up all 12. Well, carbon's octet is not complete, so we have to do a multiple bond. But notice what the 2 things are we can do. We could draw 2, we could push 2 from this oxygen and push 2 from this oxygen, and then carbon would be complete. Okay? Or we could push more from one side, one oxygen, and then the other. So we end up with a single bond and a triple bond, so we could have something like this. Okay, we still have all 14 electrons, okay? Or we could have something like this. Okay, and we've got all 16 electrons, both completely different structures, both drawn correctly. So now you use the formal charges to see which one you would use. Okay, so the first, and remember, formal charges is a bookkeeping system. It's not really anything. It doesn't mean anything except for helping you to decide which structure is more correct. Okay, so 6 valence electrons, 4 valence electrons, 6. So 6, 4, 6. Okay, then now you count up all the electrons each atom has. Lone pairs to its atom, and then shared pairs each get 1. So we've got 2, 4, 6, 7 for this oxygen. 1, 2, 3, 4, 4 for the carbon, and then 2, 3, 4, 5 for this oxygen. Now you subtract. Okay, 1, 0, negative 1. Okay, now we do the same thing over here. 2, 4, 5, 6. 1, 2, 3, 4. 2, 4, 5, 6. Okay, now we subtract. Sorry, I didn't leave much room there, did I? Let me get another piece of paper. All right, so now as we subtract these, we get 0, 0, 0. Okay, so this one reaches all zeros, and so this structure is more correct than this structure. So this is how you would draw the Lewis structure of carbon dioxide. Okay, and then an ion. One more time for an ion. All right, same rules. 6 plus 4 plus 5 plus 1. Okay, so that's 10, 15, 16 electrons we're dealing with. Okay, so let's see. Oxygen in the center, and then carbon. No, carbon in the center. Which one's more electronegative? We better look. Oxygen is more electronegative, so carbon has to be in the center. Okay, and usually it's just how it's given to you in the molecule. All right, so we've used, let's see, we've used 2, 4. Okay, so that leaves us with 12. Okay, so I'm going to complete the octets. 2, 4, 6, 8, 10, 12. Okay, we used up all our electrons. We have none left. Carbon is not happy. So we're going to just push and push. Okay. Well, wait a minute. It could be this. But it also could be this. So we've got that same situation again. Okay, so let's do our formal charges rule. Okay, let's get some different color in here. So oxygen is, let's see, 6. Carbon is 4. Nitrogen is 5. Okay, so 6, 4, 5. Okay, it looks like we might need a little more paper. Okay, now let's assign electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, so let's go 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay, 0, 0. Negative 1. Oh, wait a minute. 1, 2, 3, 4, 5. Oh, yeah, that's right. Okay, 1, 2, 3, 4, 5, 6. Okay, so we've got negative 1, 0, and 0. All right, so now it comes down to which element should have the negative 1. Should the oxygen have it or should the nitrogen have it? And it would be the more electronegative element that would have it. So I believe this should be the correct structure. So we would draw this with brackets and a negative sign on the outside. There you have it. Okay, I'll have to check on this one. I wonder if the nitrogen oxygen is a trend exception for electronegativity. So we'll have to check on this one. All right, how about if we do one with a positive charge? So here's an ion with a positive charge. Okay, so we've got 5 plus 4 for our H's plus 1. So we've got 10 electrons here. All right, so N is in the center. 2, 4, 6, 8. Okay, we've used 8. Oh wait, we don't add 1. This is an ion that's positive. We got to take 1 away. Okay, let's try this again. So 5 plus 4 minus 1. So 8 electrons. Okay, now it's making more sense. 2, 4, 6, 8. We used up all 8 electrons. Octet is fulfilled for both hydrogen and nitrogen. So we put in the bracket and complete the plus. Okay, and so there's some more Lewis structure practice.
All right. Now, sometimes it's possible to draw two different structures and still obey the octet rule. So then, how do you know if your structure, which structure is correct? See, non-equivalent, whereas the resonance structures were equivalent and blends. This is a situation where you have two totally different structures that can possibly be drawn. Well, what you do is you use this is like a bookkeeping system. Bookkeeping, it's like you see where the electrons are. You keep track of the electrons, and it's called using what's called a formal charge. Okay, so what these molecules try and do is they try and get formal charges as close to 0 as possible, and I'll explain what that means when we walk through it, or they try to have the negative charges on the most electronegative atoms. Okay, so here's how this works. You assign the valence electrons to each atom in the molecule, and then you assign the shared pairs. So lone pairs belong entirely to the atom themselves, and then the shared pairs are divided in half between the two atoms. And you do this little subtraction system here in the formal charge. And then what you do is you look at the final numbers and you see which gives you the closer values of 0 and the negative value on the most electronegative element. Now that might be a little confusing right now, so let's use an example to explain that. Okay, so, well, here's the rules again. So, take the sum of the lone pairs of electrons and 1/2 of the shared pairs. Subtract the number of assigned valence electrons from the total that you got in 1. Okay, so if we were trying this, okay, here's what we're dealing with. We've got phosphorus, and then we've got Cl and a Cl. Now these Cl's are not bonded to each other. I'm not trying to show that. I'm just trying to show what atoms we're dealing with. And then we've got an oxygen. Okay? So what are the valence electrons for each of these elements? Okay, oxygen is 6, chlorine is 7, chlorine is 7, chlorine is 7, and then phosphorus is 5. Okay, so I've assigned my valence electrons. Now I assign the lone pairs and the shared pairs. So each of these chlorine has 2, 4, 6 lone pairs, and then 1 from the shared pair, so 7. So I'm counting 7, 7, 7. Okay, so I'm putting 7, 7, and 7. All right, oxygen has 2, 4, 6, and also 1 shared pair, so 7. Okay, and now phosphorus has just shared pairs, so 1, 2, 3, 4, because they only get half of the shared pairs. All right, and now we subtract. So I got -1, 0, 0, 0, +1. Okay, now the goal is to have all these be closest to 0 as possible, And then if you have your negative values, that they go on the most electronegative element. So which is more electronegative, phosphorus or oxygen? And we see that oxygen is more to the right, and so it's more electronegative in our trend. Okay, so this formal charge here, that's what you're looking at. This is the formal charge. This molecule drawing is correct because the formal charge tells us it is. Now, of course, there's no other way to really draw this. I mean, we could put maybe oxygen in the middle and phosphorus outside, but your least electronegative value goes in the center atom. Okay, so that's how the formal charge works. Okay, so this is going to walk through it, doing the same thing I just did. Okay, but I set it up like a little table instead of how they're just subtracting it. You can do it either way. Okay, so the sum of the formal charges of all the atoms in a given molecule or ion must equal the overall charge on that molecule. So if we go back, the overall charge on this molecule is neutral. There's no brackets and there's no charge. So if we add these together, 1 plus 0 plus 0 plus 0 plus negative 1, it equals 0, which is what this molecule is, neutral. Okay? All right, now if you have a setup like this, see, both of these setups obey the octet rule. They didn't break any rules. So now you want to try and see which one is the best choice. Okay, so if we followed our rules, let's see if they give it to us. Oh, they do. Okay, if we follow our rules, okay, so oxygen is 6, carbon is 4, oxygen is 6. Now these are the valence electrons I'm talking about. Okay, so 6, 4, 6. Okay, now I count lone pairs and shared pairs. So 1, 2, so 2 lone, and then 1, 2, 3 shared. So that's 5. Okay, 1, 2, 3, 4. That's 4. And then 2, 4, 6, 7. That's 7. Okay, I subtract. I get negative 1, 0, and 1. Okay, now if I go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. I subtract. I get 0, 0, 0. So which is going to be correct? Well, the one's closest to zeros. That's what you're trying to get. And then if you do end up with negative values, they should be on the most electronegative value. Okay, so this ends our lesson on Lewis structure. So you just practice, because practice is what helps you to draw these quickly, and it just starts to come naturally. Then in our next lesson, we'll talk about the Vesper model, okay, and that's where we start to bring in the geometry or the shapes of the molecules.